You're in the Argman video channel, Real Analysis video series, lecture 15, interiors and open closed properties. So just a recap of what we looked at. So a set is closed if it's a subset of Rn and all sequences in that set that converge to a point x, that x must be in A. For it to be closed, it's open if it has every element. There's a radius greater than 0 for every element such that the open ball centered at that element is itself contained in A. And the closure we defined is the smallest closed set containing A. We didn't define it this way, but we showed it. The definition was that it contains all of A's limit points. And as an analog to that, let A be a subset of Rn. The interior of A is int A, and A. It's basically everything, every set in A with which you can put an open ball around. A contained in A. And one obvious property is that the interior is contained in the set. And so much how we showed the closure was the largest closed set containing A. The interior is the largest open set contained in A. A bit of a dual property. And A is the largest open set contained in A. Moreover, A is open if and only if A is equal to its interior. And the proof for this is similar to the one for closures being the largest closed set or smallest closed set containing A, so we won't repeat that again. Example, if you take this closed interval and union it with a single element, so that single element set of 2 is itself not open, so it wouldn't be in the closure, and the endpoints 0 and 1, you can't put an open ball around them, so they wouldn't be in the closure, but everything else you could put an open ball around. So and A is equal to 0, 1. And if you take the interior of the integers, you couldn't put an open ball around them, since if you say just drew them out, value -1, 0, 1, and so forth. No matter what, you could not put an interval around it such that it would be in the integer still for any radius greater than 0. So the radius can't be 0. So that is just equal to the empty set. So a theorem. We're going to look at properties of open balls, open sets, of open sets. If A is a subset of Rn, the following hold true, the following are equivalent. A is open. A is a union of closed balls. And if you take away A from Rn, that itself is closed. So proof. 1 if and only if 2. We saw this last lecture. If A is a union of open balls, then A itself is open. Now suppose A is open for the other direction of the proof. Open implies union of open balls for A and A, any element. There is a radius greater than 0 such that it's contained in A, just by definition of open. Then if you take the union over every element, it's going to be a bit confusing notation, but that radius is dependent on the A, and it's censored at A. That is exactly A itself. Now let's show 1 if and only if 3. So A is open if and only if the complement of A, taking away A from Rn, is closed. Suppose A is open, we show, I'm just going to write this down because I'll be scrolling down for some room. Suppose that the sequence is in there, the complement. Then if it has a limit point in Rn, we're going to show that it must be in the complement. So let's suppose that it is in A itself. Since A is open, there must be a radius greater than 0 such that the open ball censored at X of radius R is contained in A. Since that sequence converges to X, there must be an XM such that XM minus X is less than R, just by definition of convergence of in Rn. So this must be that XM must be in ball, which is a contradiction, since XM must be in the complement, so it can't be in A itself. So X must not be in A. Oh, I don't want that. So X must be in the complement of A, Rn set minus A. So every limit point must be in the complement, so that means the complement itself is closed. Now for the other direction, you want to show closed implies, the complement being closed implies A is open. So let's label it like that, label it like this for the other direction. Suppose the complement is closed. Then, since it is closed, every natural number m, there must be something in the complement such that this holds. And we get this inequality just from convergence to X, M, or to A, because 1 over M is positive, so this holds, where A is in A. Then xm goes to A, so we're assuming A is in there. So we have a limit point in A, since Rn A is closed, that must also be in the complement since it contains all of its limit points. And that itself is a contradiction, with A being an A. So there exists M in N such that if you take the 1 over M ball around A, that is in A. So we can conclude that A is open, since it's just the definition of being an open set. Completing our proof. So we prove 1 implies 2, 2 implies 1, 1 implies 3, 3 implies 1. So if you chain them up, you can prove any one if any of them is true. So a little remark. If A is closed, then if you take the complement twice, that is closed, and this is just A. So this would mean that this is open. So we get that for free from the previous theorem. And to sum up everything, or to have some more properties that might be useful, the closure of the union or the intersection is just the intersection of the unions, or the closure of the intersections. So if this looks like De Morgan's laws to you, if you've done that sort of algebra before, be careful, because these are pretty different from that. I just write them out. it'll probably make more sense if you just read them than me reading them out. Intersection. Okay, and as usual, when we have these many like propositions, we won't prove them all, we'll just prove a couple. So assume int a, well, that's just true, right? So this must be true if you take the complement. Because if you take the complement, the subsets flip. Since this is open, just from definition of it, this must be closed. And since we know the closure is the smallest closed set, I don't know how to fix it when it goes like this, so I'll just keep going. We have this direction. Oh, that's too long. So now we'll show the other containment to show equality. Let me just label that. Maybe highlighting it would be best. Now we're showing this direction. So let there be something on the right hand side, Rn set minus NA. This must mean that X can't be in the interior, just by definition of a complement, for every natural number M. You can construct a sequence in the complement such that that is contained in the 1 over M ball surrounded in X. Thus, since the radiuses go to 0, it must eventually end up at X, which means that X is in our N complement A closure. So we have the other direction. So just to write it out, we can conclude that they're equal because one contains the other, and if you go the other way, you also get containment, so we get equality. All right. Let's cap it off with a couple examples. if you have this open interval and this open, this other open interval, the closure of their intersection will be, since their intersection is empty, the closure of the empty set, and the smallest closed set is containing the empty set is itself the empty set. And we get that closure of empty set is equal to empty set for free, just because we know the empty set is closed itself. But when you take the union of their closures, or the intersection of their closures, and you got the intersection of the closed intervals, which is non-empty. So don't get confused and split that closure across the intersection. And as another example, take these closed intervals from 0 to 1 and from 1 to 2. The interior of their union is equal to the interior of the closed interval from 0 to 2, which is 0 to as an open interval. Now if you take the union of their intersections, then we get that these open intervals union together, and there's no way to simplify it, so that's the final answer. So to sum up those last two things, we get that A union or intersection B is not equal to that, and similarly you switch that to a union from an intersection and closure to an interior, then that is not equal to the interior of each union with the other. And that's it for this lecture. Thanks.